I welcome you all for another presentation on electronic devices and circuits. We are discussing about the various classifications of material based on their energy band structure or energy band diagrams. Since last presentations, if you recall, we have seen the materials, like insulators and conductors and then semiconductors. And we have seen certain differences, means how is their energy gaps and how that energy band gap or energy gap will depends on the temperature and how it varies with the temperature, right? In today's presentation, we will see the conductivity of a semiconductor due to both the electron as well as the hole. Thereby, we can see the total conductivity of a semiconductor. It is a very simple mathematical relationship, and based on this formula, there is a mathematical formula actually. So based on this formula, so definitely the questions may be expected in competitive examinations like GATE as well as IAS examination, right? We will see about these total conductivity of a semiconductor in this presentation. Let us go into the subject. We will see that relation. Yes, in this presentation, we will see today the conductivity total conductivity of a semiconductor, right? So in previous presentations we have seen the conductivity from that Ohm's law. We have seen the Ohm's law, that is nothing but from the conduction current density. We have seen the definition of conduction current density. I think you have remembered this. Conduction current density, capital J, is equal to, what is the formula? Anybody? Right? Remember, J is equal to N into Q into Vd. N is the concentration of electron, Q is the charge of electron, Vd is the drift velocity. This equal to N into Q into, what is Vd? We have seen that Vd is equal to mu into E. This relation you must remember. Vd is equal to mu E. Therefore, substitute here mu into E. This is what general definition of a conduction current density. Ampere, okay, per meter square. This is ampere per meter square. Is it not? N into Q into mu E. This is the general. Whereas, if you consider a semiconductor, we are talking about the semiconductor. So this is general formula for conduction current density, right? So if you consider the semiconductor, in semiconductor normally, if you recall the diagram, means it is, this is the energy gap. Let us just recall. This is your VB, means valence band, and then this is what your conduction band, and this is what your energy gap, or also sometimes called as forbidden energy gap also. Easy also called the forbidden energy gap. Remember that, right? So initially, whatever the free electrons available, those are there, those are lies in this valence band actually. Say for example, you may have certain electrons, 4 electrons, let us see. So after application of the electric field, so these electrons slowly moves from here to conduction band actually. Thereby you will get a small, a empty space here, a circle. Means whenever the electron moves from here to conduction band, you will get empty space there. Means you can say absence of electron here. Means already electron moved from this valence band to the conduction band. Thereby you will have a empty space there in the form of circle. This empty space is called as hole. This empty space is called as hole. So this thicker one is represented the presence of electron. Therefore, as you know that the electron concentration is represented by N, the electron concentration is represented by N and the hole concentration is represented by P. Okay, N is the electron concentration, right? This is the electron concentration, right? P is the hole concentration, hole concentration. Now, individually, with respect to both electron and then holes, we can define the conductivity individually. The definition of conductivity individually with respect to both electron as well as hole. So, if you consider the electron concentration, in that case, you will have J is equal to the conductivity. Now, the current density is called as conduction current density with respect to N. Means you must write J suffix N. J suffix N indicates that the conduction current density with respect to electron. What is the formula? Same, whatever we have seen just previously. It is N into Q into mu into E generally, right? Where N is the electron concentration, Q is the charge actually, and okay, mu is the mobility. But here, as we are considering with respect to electron, then you can write here mu suffix N, means this is the mobility with respect to N electron. This is the, now this is called the conduction current density with respect to electron. This is the conduction current density with respect to electron only. Means the electron concentration multiplied by the charge into mobility of electron and then E. And from here, you can write that this is called as sigma E. This is called Ohm's law. This is J suffix N. Then you can write here sigma suffix N. Sigma suffix N. Right? Where sigma N is equal to, where sigma suffix N otherwise is equal to this portion, N into Q into mu N. You can write N into Q into mu suffix N. This is what your conductivity with respect to electron. This is the conductivity with respect to electron. Sometimes in examination, they will ask you only this much only. What is the conductivity with respect to electron? Right? Then you must use this formula only, N into Q into mu N. You must need the electron concentration and then the mobility of the electron. If you know these two parameters, N into mu, then with this, if you multiply, okay, these two along with the charge of electron, that is 1.609 into 10 power minus 19 coulombs. That is the charge of, the magnitude of charge. Okay, now then if you multiply with these, then you will get value that is called conductivity with respect to electron, right? This is what with respect to the electron actually. Now, okay, this is what the conductivity. And similarly, if you consider the hole, then with respect to hole, then you can write the same conduction current density due to hole. Okay, then I will write the expression for J suffix P. J suffix P is nothing but the conduction current density, with respect to hole. So in the same manner, you write there, here as it is for electron, we are considering N. It is with respect to P, therefore instead of N, you will get here what? P. You will get P. Q, obviously Q will be there in both of the cases. Q is a common actually. Q is a common, and here you will get mu suffix P. Mu will be there, but mu suffix P. E is common again. E is electric field, right? Therefore, J suffix P is equal to P means the whole concentration multiplied by Q into mobility into E. So, in this case, this is called your conduction current density due to hole. This is called conduction current density due to hole, and furtherly this can be written as J suffix P is equal to, it is sigma into E but P, sigma suffix P, right? What is sigma P here? Your sigma P means conductivity due to hole is equal to P into Q into mu P. That's it. Q into, okay, P into Q into mu P. This is the conductivity with respect to hole, right? This is what the conduction current density with electron. This is the conduction current density with the hole. So in any semiconductor, right, in any semiconductor, the total conduction current density is nothing but the sum of the conduction current density due to electron as well as the hole, right? This is individual actually. This is with respect to electron itself, this is with respect to hole itself. Now for any semiconductor, if you consider, you must write the total conduction current density J. Now you can write the J is equal to what actually? What is J actually? What is J? J is nothing but for any semiconductor, the total, right, the total conduction, the total conduction current density. What? Current density. This you can write as capital J. That is nothing but J is equal to, it is J suffix n plus J suffix p. J suffix p, J suffix n, J suffix p means that the total conduction current density is nothing but sum of electron conduction current density and then hole conduction current density. And further this can be written as, it is J is equal to, this is total. What is J in actually? It is n, right? It is Q mu n into E plus, this is what Jn, basically this is what your Jn, right? What is Jp? It is P Q mu suffix P into E, right? This is what your Jp. This is what your total conduction current density. This is the total conduction current density, right? Now from this relation, you simply can write that, what we can write here? So here if you take QE is common in both of the cases, no? In both the Jn and then Jp, if you see, QE term is common actually in both. QE is there in this as well as Q into E is also there in this. Therefore, if you take J is equal to, you can take Q into E as common, take Q into E as common, then you will get N into mu N plus P into mu P. And this is equal to, now you can write sigma into E. This can also be written like this, J is equal to sigma E. Therefore, what is here sigma? Where sigma is equal to what actually? This one, Q into E. E is already there, no? Here, other than E, what is the rest part? Q into the remaining part. N into mu N plus P into mu P. Right? This portion, right? Sigma is equal to, now this entire thing can be written as like this, J is equal to sigma E, again in the form of Ohm's law, and where sigma is equal to Q into N mu N plus P mu P. What is this? You know, this is called the total conductivity. This is called total conductivity. This is the expression for total conductivity. Therefore, sometimes it can be given that the electron concentration will be given in the problem as well as the hole concentration will also be given in the problem, and along with their mobility values, the electron mobility will be given and the hole mobility will also be given. Then you will be asked to find out the conductivity, the total conductivity, total, J suffix total you can write. Total conductivity or total conduction current density, they can ask anything. If you remember these formulas in a systematic manner, and definitely you will get the answer without any confusion, right? This is called now total conductivity of a semiconductor, total conductivity of a semiconductor, right? And in most of the cases, if you write again in the semiconductor, we have two classifications of semiconductors, right? If you consider the semiconductor, again we have two types of semiconductors basically, right? What are the two types? You know, types of semiconductors, if you see, one is the intrinsic semiconductor. I can write the types of semiconductor. Types of semiconductors. types of semiconductors, right? So in types of semiconductors, we will have two types basically. One is intrinsic. What? One is the intrinsic semiconductor, right? This is also called as pure semiconductor. This is also called as pure semiconductor, intrinsic or pure semiconductor. And the next classification is extrinsic. Extrinsic. Okay, EXTRI. Okay, NSIC, extrinsic semiconductor, and also called as extrinsic semiconductor are called impure. This is called impure semiconductor, right? These are the two important classifications of semiconductor. One is the intrinsic semiconductor, second one is the extrinsic semiconductor, or impure semiconductor, right? If you consider the pure semiconductor first, the very important property of a pure semiconductor is nothing but the electron concentration is absolutely equal to the hole concentration. N is equal to P. That is the relation, okay, will be applicable for pure semiconductor or intrinsic semiconductor, right? The electron concentration N is exactly equal to the concentration of hole. Therefore, N is equal to P in this case in intrinsic semiconductor. Thereby, as N is equal to P and this is equal to, I will consider something else now, let us see. So, in intrinsic semiconductor, your N is equal to P. Therefore, as these two are equal, N is equal to P, and the equivalence is, I will call as N suffix I. I can represent one particular letter, that is N suffix I, where N suffix I is called as intrinsic carrier concentration, right? N suffix I is called as intrinsic carrier concentration. This is for the pure semiconductor only. Therefore, you apply this relation in this equation wherever N is there. So, in place of N, you write N suffix I, as well as wherever P is there, you write N suffix I. Therefore, what you will get, if you substitute that value of Ni in this expression, you will get sigma total, means sigma is nothing but conductivity, means total conductivity is equal to Q times, what is N? You can write N is equal to P is equal to Ni. Therefore, N is equal to Ni, P is also equal to Ni. Therefore, in place of N, you write N suffix I, right, into mu N. Clear? Plus P, what is P? P nothing but again Ni, N suffix I and then mu P. Clear? Then this equation furtherly can be reduced as, how? This equation can furtherly reduced as this equal to, now Ni is there, here also Ni is there. So take outside that also, Q into N into I, right? This is equal to mu N plus mu P. This is sigma total. This is what actually, that, okay, conductivity of a pure semiconductor. This is the expression for conductivity. This is the expression for conductivity in case of pure semiconductor. So, if the problem is given based on the pure semiconductor, so you must read the problem very carefully. What is they are asking in the question? Whether they are using the word pure semiconductor or simply semiconductor. There is a little bit difference is there between these two. If they are asking pure semiconductor or intrinsic semiconductor, then if they are asking based on this conductivity, you must use this formula, Q into Ni. So Ni will be given definitely, don't worry about it. If it is based on this pure semiconductor, and definitely it will be given. The Ni is a constant basically, carrier concentration value is a constant, basically they will give this value. Therefore charge value also they will give. Only you need the mobility of electron and mobility of hole, and even that value also they will give. Means electron mobility, hole mobility, and this is intrinsic carrier concentration multiplied by the charge of electron. Hole gives the total conductivity of intrinsic semiconductor, right? So this is what about the conductivity of n-type, due to electron, as well as the conductivity we have seen due to holes also, and then we have seen the conductivity for the pure or intrinsic semiconductor, right? I think we will finish off this presentation here, and I hope you all understood this, okay? And we will see some more the further continuation of this in the subsequent presentations, okay? Thank you for watching, right? Have a wonderful day.